Okay, I'm going to be continuing from where I left off, calculating molality. So molality is similar to molarity, except we use a lowercase m to represent that. And it's still moles of solute in the top here, so this was whatever substance I'm going to give you the formula of. However, the bottom part here, it's measured in kilograms of solvent. Again, 99% of the time, the solvent is going to be water. So the question is, what is the molality, so little m, of a 5,000 milliliter solution made from water, and it contains 67 grams of NH4(2)S. So remember, if we're calculating molality, look at the relationship between the other two variables. If you are using the triangle, that is going to be moles over kilograms. So in this problem, again, the solution is made from water, so that's our solvent. And then we have our grams, which we'll need to convert into moles for our solute. Now, I realize this says 5,000 milliliters of water. Now, I know I said earlier you can't convert between different base units. However, this does work if you know the density. So water has a density of 1 gram per milliliter. So that's the same as saying 1 gram equals 1 milliliter. So this means if you were to measure out 1 milliliter of water and you were to weigh that on a balance or a scale, it would weigh 1 gram. That's because that's water's density. Are all other substance or liquids like that? No. But this is true for water. So therefore, if you have 5,000 milliliters of water and 1 milliliter is equal to 1 gram, that's the same thing as saying you have 5,000 grams of water. Now again, notice I didn't move the decimal. I did a picket fence for something like that. So if you can move the decimal, if you're converting between the same base units, but if you're working with two different units entirely, you're going to have to use a picket fence. However, you can also use a picket fence or moving the decimal when it comes to metric conversions. So when in doubt, you can do a picket fence. Now, this is in grams, but I need to convert it into kilograms. So I would move the decimal 1, 2, 3 spaces to the left. So that would be, this is equal to, this would be 5 kilograms, which makes sense because there's 1,000 grams in 1 kilogram. So if you have 5,000 grams, that's the same thing as saying you have 5 kilograms. For the solute, we're going to have to convert that into moles. So in order to do that, we have to find the molar mass. So again, pause the video and try to calculate the molar mass of the substance. So this one's a little different because we have the first element right there. The NH4 has the 2 on the outside of it. So again, that 2 gets distributed to everything inside of it. So nitrogen is 14.007. 2 times 1 is 2. Plus 2 times 4 is 8. So there's 8 hydrogens and 2 nitrogens. And then plus we have sulfur. I think it's 32.06. Let me check. Sulfur is 32.06. All right, so we have 14.007, which is nitrogen. There's 2 of them times 2. Plus hydrogen is 1.008 times 8. There's 8 of them. Plus there's 1 sulfur, 13.06. So 68 0.138 grams is equal to 1 mole. And then that number we're going to plug in the top. So 67 divided by that number, 0.98, 3298. 3295999 moles. Then we're going to divide that by 5. 0.19, we're going to go 4 significant figures, 6, and then that will round up to a 7, and we use a little m to represent molality. Lastly, I'm going to go over double replacement reactions. So for this, you will need the back of your periodic table, which has the charges on it. So these types of reactions are when you combine two compounds with each other. Most likely these are going to be two solutions, and they're going to be ionic compounds. So most likely they're both going to look like two clear solutions that you're combining together, and then you're looking for if there's a reaction or not, which this is something that we have done before. And in chapter 13, we'll talk about how do we figure out if a precipitate is going to occur, if a reaction occurs, or if it doesn't occur. And we're going to be doing that by using this type of equation, reaction, and a solubility chart. But first, let's review these types of reactions. Again, for now, let's just assume that these are going to happen. So in a double replacement reaction, you are going to switch like with like. So if you ever look at a chemical formula, the metal is always written first. So these are going to be all ionic compounds. So they are all going to be things that are found on the left-hand side of the periodic table. That is always written first, the metal that has a positive charge. The second element is going to be some type of a non-metal. So something on the right-hand side of the periodic table, or it could be a non-metal that is found on the back of your periodic table, which is one of your polyatomic ions. Yes, these are covalent compounds technically because they're made of two nonmetals. However, they do have an overall charge, making them an ion, and therefore making these ionic compounds. So what we're going to do is I always like to switch the first two elements with each other. Okay, so we're going to switch the first two, just like you see in this diagram here. If we have A, B, C, and D representing those different elements and their compounds, you're going to switch the first two, which are the cations. Those are technically the positively charged ones, which are always your metals. And then B and D, those are, so A and C are representing the metal, the cation, the positively charged part of the compound. B and D are representing the negatively charged ion, or the nonmetals that make up the compound, which can be a nonmetal on the periodic table or a polyatomic ion. Notice that there's only one, which I have already kind of shown you here, one positively charged polyatomic ion, which is NH4. It's the only one we're going to be using. All right, so I'm just going to write what elements go with each other, and I'm going to just write that down here. My final answer I'm going to write here. So Na is now going to be with Cl, should look familiar, and Mg is now with OH. So that's the first thing. Put the things that go together. And later I'll get to this stuff. That's later. Next, we have to put the charges on all of these and then do the crisscross. So Na, so this is on the front of your periodic table. So remember those charges at the top of each group. So Na has, let me actually pull up a periodic table. Let's see. Let me just pull up the Word document. All right, so again, make sure you're looking at the top of your periodic table. So Na, that has a charge of +1. And then Cl has a charge of -1. And then we do the crisscross. So again, this is a quick, easy way to determine the formula of a ionic compound. So the number will become the subscript. So there would be a 1 that goes here, not the charge, just the number. And there's a 1 that goes here. However, we don't write the 1s. We don't write 1 and 1. We just don't write any number. So that would be NaCl. And that makes sense because if these two are together, one has a positive charge, one has a negative charge. Overall, that's a charge of 0, which is what we want. So that's the first compound. And it doesn't matter. I could have written this one first, but I just decided to go with this one first. The order does not matter. Magnesium, this on the front of your periodic table, this has a charge of +2. If you ever see something that has more than one element, you need to look on the back of your periodic table. That is a polyatomic ion. So we have OH, which is hydroxide, and that has a charge of -1. -1. So when we go to do the crisscross for this one, so the 1 will go here. So it is just Mg for magnesium. However, this we're going to have a 2 going here. Now remember, with polyatomic ions, you always want to put them in parentheses and then put that number on the outside. If you don't, this is incorrect. That's not, that 2 then is just getting applied to the H. You want the 2 to be applied to the entire thing. And this makes sense. Magnesium has a charge of +2, and each OH has a charge of -1. So overall, this would be a charge of 0, which is what we want. That's another way to look at this. Again, the crisscross is just an easy way to determine the formula of a ionic compound. All right, so let's do one more. So again, I'm going to switch the first 2 elements with each other, and I'm just going to write what goes with what. So the K, potassium, is with the Cl, and then the Ba, that is now with the CO3. So just write the things that go together. Next, we're going to write the charges on these. So again, most of these you can find on the front of your periodic table, and if it's something like this with multiple elements, you need to look on the back of your periodic table at the polyatomic ions. So potassium has a charge of +1, chlorine has a charge of -1. So again, if you have the same charge on each thing, so let's say you had, I don't know, Ca, which is +2, and then oxygen, which is -2. If you end up having the same charge, you don't want to write it like this. You still want to simplify it. So if you have 2 elements or 2 things that have the same charge, then there's your formula. You don't have to change anything. You just write the 2 things that go together, because if you have 1 of each, then your overall charge will be 0. Next, we have Ba and CO3. So actually, this is a good example of this, because Ba has a charge of +2, and then CO3, let's see, CO3, which is right here, carbonate, has a charge of -2. Now again, since they both have the same charge, so some of you might think, oh, I would write it like this. Okay. However, they both have the same charge. So we're just going to simplify it to this. BaCO3. And then when it comes to balancing, you just have to make sure you have the same number of each element on either side. So I will make one more video to go over balancing chemical equations.